Hello, this is Chenmin from Intel, and my today's topic is RT flow optimization in i40e driver. Here's the agenda. First, I will introduce the background. What is the RT flow and the RT flow use cases? And then is the i40e RT flow implementation review. And next, I will introduce the optimization solutions that includes the hardware-specific optimization and software optimization. And at last is the summary. So what is RT flow? We have had two talks yesterday that I think you have already know that what is the RT flow. So this is, here is just a brief introduction. The RT flow provides a generic means to configure hardware to match specific ingress or egress traffic, alter its fit, and query related counters according to any number of the user-defined rules. Here's the RT flow use cases. First one is OVS. Matthew have did a very good presentation last afternoon, so you have already know that the OVS leverage the RT flow to implement its partial offload. And in fact, it does not really care the result, but the update rate should be as faster as better. And another scenario, another use case is the FIDO VPP. A typical use case is the UDPI project. It cares the result, but do not need a very high speed update rate. So here comes the challenges. In our original design, we didn't consider the requirement like OVS, so the code is not fully optimized for this high-speed update scenario. That's why I did this work. Okay, here's the RT flow i40e driver implementation in the DPDK. It may be a bit different from that in the kernel driver. And from a high-level perspective, there are three main parts. First one is the software preparation. I marked in the orange. And another one is the hardware necessary part. I marked in the blue. And the last one is the synchronously waiting to retrieve the result from NIC. I marked in the green. Okay. Here's the cycles consumption pi. We can see that the synchronously waiting takes most part of the time. So it is clear to investigate the problem. Is the synchronously waiting a must? And is it possible to change it to asynchronously? And how to minimize the software preparation time so that we can achieve the hardware's highest update rate. So let's take one by one. For the first question, the answer is yes. Okay, and first let's see how is the RT flow implemented in the NIC and DPDK. Here is the RT flow implemented in the implementation in the NIC. i40e is the driver for Intel X700 series NICs. In this NICs, it uses the flow director to implement the RT flow. The flow update packets are running in the fast path, and we can see that the host there on the left it can continually send out the raw packet to the NIC, and the NIC will report the error status if there's a programming failure to the host. We can see that the green block. So theoretically speaking, the insertion can reach a very high rate. Here is how it is implemented in the DPDK. First step, we will construct the raw packet in the buffer, and then second step, we will fill the TS descriptor points to the buffer, And step 3, we will update the tail register to tell the NIC, hey, there's a new packet is coming, and the NIC will come to fetch the raw packet from buffer at step 4, and then cite the DD flag in the TS descriptor in step 5. Okay, then the software knows, okay, let me check if it is successful or failed. Then step 6 and 7, the software will busy loop there, wait for a potential error report from the NIC. For this module, to implement a synchronous module, to implement a synchronous module, we have 2 problems. One is how to avoid the buffer overwriting in this step 1. Suppose that the software directly returns after the step 3, and immediately insert a new flow and start overwriting the buffer in the step 1. But at the meanwhile, the NIC is still fetching the last packet, the raw packet from buffer. Then this may lead to errors. And the second problem is, if we discard step 6 and 7, then how to retrieve the programming status from the NIC? So let's see how to solve these 2 problems one by one. It is easy to solve the buffer overwriting problem. I initial the 128 descriptor buffer pair, and each TS descriptor is fixed point each TS descriptor is fixed point to the buffer. So let's see the new progress. At first, the same. We just construct the packet in the buffer, and then fill the TS descriptor 1, which points to the buffer 1, and then update the tail register in the NIC to tell the NIC that there is a new row coming. Okay, and the NIC will comes to fetch the packet from buffer 1 and start programming. Okay, the software will directly return without waiting for the DD flag and the error reports. Through other mechanisms, we can make sure that the program will be successful, and I will introduce this mechanism later. And then the software use the second, the third descriptor buffer pair to insert the new rows. The NIC will process one by one. And next time, before reusing this descriptor, we have to check and wait the DD flag first to make sure the descriptor is available. See step 0. Okay, so by using this pipeline, software can safely asynchronously send the raw packets to the NIC. Okay, and let's see how to solve the next problem, retrieving the result from NIC. Before understanding how to retrieve the programming status, let's see how is the internal resource management of the flow table in the NIC. Each PF gets a private space called the guaranteed space, and there's a shared space for all the PFs. At filter programming, the hardware will try both spaces. First, it will try the guaranteed space until it is full. Then it will compete with other PFs in the shared space. So for these guaranteed flows, I mean that the flows that will be inserted into the guaranteed space, we can make sure that the flow can be inserted successfully. But for those shared flows, we have to retrieve the result from the NIC because there is a competition. So can we do it better? Yes. At filter invalidation, the budget is gained back to either the guaranteed space or the shared space. I changed the default behavior to make it being greedy. Means it will return the budget to its own guaranteed space first. So the next several new flows, which is followed by some deletion, can be inserted into the guaranteed space. Here are some snapshots to show you how it works. At first, we already have 512 guaranteed flow and 100 shared flow. And then I destroy the flow 1, which should be in the guaranteed space. See, the guaranteed space, the guaranteed count decreases 1. And then I destroy the row 600, which should be in the shared space. And so we can also see that the guaranteed space decreases 1. This is because the budget is gained back to the guaranteed space. And then I create a new flow. We can see that it is inserted into the guaranteed space because there's available room for the guaranteed space. So as the flow table is continually updated, more and more flows will be inserted into the guaranteed space and being accelerated. At this point, we have tried our best to asynchronously retrieve the result. And here's the hardware and software and hardware consumption pie. We can see that the software takes up most of the time. So our next work is to optimize the code to reduce the software percentage. Okay, let's take a look at the software insertion flow. When calling RT flow create, the first step is to malloc struct RT flow. This will be returned to the caller as a handler. And then in valid function, we will pass the pattern, the attribution, the action to make sure that it is a legal flow for this NIC. And then we will also configure some input set registers, means to tell the NIC that the format of the coming row packet. And next one is software lookup. The software will maintain a hash table and a linked list for all the inserted flows. And so in this step, the hardware will look up from the hash table in case there is not a conflict flow that has already been inserted into the NIC earlier. Then construct the packet and send it to the NIC. Okay, at last, the software will malloc a piece of memory to share the flow, to store the flow information that includes the input set, the attribute, and the action, and insert it into the linked list. Here are the key consumptions. We can see that the validate function takes most of the time, but I will introduce how to optimize it at last. Let's see what else can we do to optimize the other parts. Okay, we can see that there are two malloc dynamic memory allocation in the software flow, which may cost much time in general. So I introduce the usage of memory pool. Instead of malloc and free every time, I use a bitmap to manage a pre-allocated memory pool. We can see it on the right. So when creating, we can pick up an unused block from the memory pool with an index attached and return the address of the RT flow to the caller as handler, and then mark the corresponding bit to used. And when deleting, we can mark the corresponding bit to unused. Then, as we have already know that i40e uses a linked list and a hash table to store all the created rows. And for each new row, it will first look up from the hash table to make sure that there is no conflict row that has been already inserted. And then insert it into the hash table and the linked list after program is done. we can see that on the left, there's a hash lookup under the right circle, and there's another RT hash add, which has a similar lookup operation inside on the right. So we can merge these two operations. We can see the new flow on the right. We directly try to add the flow into the hash table. And if there's an existing key in the hash table, means there's a conflict flow. We just return error. Else, this is a new flow. Then we just add it into the hash table. Then the hash value can be used to index a pre-allocated buffer to avoid the dynamic memory allocation. Here are some other optimizations that can benefit the validated function. I put it here. First, we can catch some registers in the software to avoid the overwriting the same value again and again. And then we can catch some configurations so that we don't need to read them from firmware each time. For example, we have a TPID here in our code, and in my refactored code, I catch it into the software so that we don't need to read it every time. And then we can adjust the code order to put the similar code blocks as close as possible to make the most efficient use of the instruction cache. And at last, the flow also has the locality. So we can catch some regularly used flow tabs to save the parser function searching time. Here's a comparison. We can see that although the software still takes a bigger part, but the percentage has been reduced a lot. And in the average case, we can get a very good improvement. And for the best case, we can see a very huge improvement there. OK, here's the summary. In this talk, I introduced the RT flow optimization in the i40e drivers. I analyzed the flow insertion process and the resource management and found out that we can asynchronously retrieve the result in some cases. And at last, I introduced some best known method for the software optimization. And at last, I presented the performance improvement. So thanks. Here's my email. You can have a discussion with me if you have any questions.
So what is the performance of rule update you are able to achieve while inserting rules from the data path?
In fact, it is really depends on how long time you wait for to retrieve the result from NIC. It depends on your workload and your platform.
Let's assume I have application that all it do is insert rules. What kind of insertion rate it will be able to achieve? What was before and what is now?
Okay, before there's a lifelong time to make sure that anything is fine because we didn't consider the requirement for this high-speed update scenario. So this is a very, very slow. And for the refactored code, we can asynchronously retrieve the result in some cases, so the performance is better.
Yeah, but what is the numbers? What
is the numbers? Okay. Okay. So in the average update rate, we can the update rate is several thousands per second, and but in the original code.
what is the number? What is the Y scale on the best case?
In the best case?
Yeah.
In the best case means that all the flows will be inserted in the guaranteed space. So the performance is very, very high, around about 1 million rows per second.
1 mega rule per second?
But we don't have so much guaranteed space.
So in theory, so in theory, if you can insert 1 million runes to your hardware, it can be.
No, we don't support.
Yeah, in theory, I mean the capabilities you show here, it's like you can support in software up to 1 million rules per second if hardware would support that.
Yeah. Okay.
Okay, please, can you go back to your slide with mempool and bitmap?
Bitmap?
Mempool.
Mempool.
Yeah, when you put all the RT flow rules in mempool. Yeah, this one. I don't understand why you use mempool to save your flow rules.
Okay, because in our original code, we use malloc to apply for the memory from the DPDK memory pool, and that is a generic method, and it's not very fast. So I use the bitmap to manage my memory pool here to accelerate.
Yeah, but you accelerate with your bitmap. So yeah, all these RT flow structs are in the same mempool object, right?
Yeah.
So this object could come from malloc. It would be the same.
From
malloc.
Either
you allocate your object with mempool or with malloc. I don't see the difference.
Okay. This is a pre-allocated buffer that it is mallocated from the memory pool when initialization.
Sorry?
I mean, this memory pool is initialized when this module is initialized, so we can retrieve it when we want to use the memory. So.
Okay, maybe I can help Chenmin to answer questions. Like that, the i40e driver, the flow director is using like a transmit ring. So the transmit ring, we generally think it about a slow path before the OVS offload, such things happened. So, but right now, the program rate needed to be increased, right? So the hardware has this capability to program the ring fast. And then I think Chenmin is take the knowledge about how to transmit the packet fastly. So this memory pool is pre-allocated in the driver. So it can speed up to get the memory from the memory zone, such like that.
Yeah, I think I get it, but you can do this pre-allocation with malloc too.
Yeah, that might be an option. Yeah.
It just looks strange to use mempool and do a nested mempool inside with bitmap. This is like a 2 levels memory allocator. And either way, if you really want to use a mempool, use a dedicated mempool.
But the DPDK memory pool is not fast enough for my case. But it's because that is the generic usage. Okay.
Okay.
Mm-hmm.
I have one question, which is, so it's kind of related to RT flow in general. Is there some API that you could think of that would help the applications know what's going on better under the covers? It seems like the hardware is doing a lot of work and to try to help the application, and maybe we could ask the application to do some of the management itself.
You mean can we add some?
I mean, I don't know. I mean, something where you can tell how many flows you have left, or some you know, it's a cooperation. Flow management is a cooperation between the application and the hardware. And right now we kind of have a one-way communication from the application to the hardware. We don't have any back channel at all about what's going on in the hardware to the application, like what's being used, what's not being used, how many you can take. I mean, validate is kind of like the C compiler. It tells you that I could compile a program. It doesn't tell you whether it'll run.
Okay, I think that's a good idea. But as you all talked yesterday, adding new APIs may break the API and the API stable.
Actually, adding new APIs in general is okay. It's
in general.
It's adding new fields into existing structures. So if you add a new call, RTE flow data extract, and it returns a new data structure, it's a new data structure into a new API call. It's not a problem. But if you change the format of the RTE flow structure to add a new field into what an RTE flow rule is, then that would be a problem.
Oh, okay. I think this is a good idea.
I was just hoping that you would say that you looked into it, because I think that's a general problem. Trying to use RTE flow is hard. Anyway. Any other questions?
Okay.
We have. All right.
So
Thank you very much.